Like this is working. Yeah, so Kenny wanted me to call this drone radar. I put a little caption underneath, radar-equipped UAV systems and their role in providing additional coverage and improve the measurements of the ice sheet. And so let's move on to the outline. And I'll start out just giving an overview of radar measurements of ice sheets. And then look at the application of drones to sensing of snow and ice. Look at some recent activities from both other groups and what we've done at CRESIS. Talk about some of the lessons learned. And then maybe look at drone radar application more specifically in terms of what we want to get accomplished for rings. And then talk about some future directions, and I might propose a couple of recommendations on how we could move forward. These are a couple images that have shown up in a number of presentations. And this is kind of the typical using radar systems to map the ice sheet. And so we have a platform here that has radar systems operating at a number of different frequencies, from HF or VHF all the way up to maybe Ka band. And what we see is we're able to map the ice column at various depths and resolutions. So for the lower frequency systems, we're able to see down to the bedrock at somewhat coarse resolution. As we move up in frequency, we're not necessarily able to see all the way down to the bedrock, but with better resolution, and this might be the accumulation radar. And then we get up to the snow radar, which we're able to start looking at annual snow events and mapping accumulation. Now, when we start considering the ice sheet margins and measuring ice thickness, it's more important to look at systems in the HF or VHFs where we're able to get past the attenuation and the surface roughness and get an indication of the bedrock. So, application of UAVs to radar sounding of ice sheet, and we're looking at, with advancements in drone technology and high-speed electronics, the use of radar-equipped drones for routine sounding of snow and ice is becoming more realistic to the wider polar community. And this is both drone technologies, efficient engines and batteries, vertical takeoff and landing, and also open source flight control software. And also radar technologies. We've seen an explosion of software-defined radios, and also miniaturization of multi-channel electronics, both for 5G and 6G, as well as the defense industry. And what we see over there on the right is there's a number of these vertical takeoff and landing drones, which provides us an opportunity to deploy these in remote locations. And then on the bottom there are new electronic devices, and we have a Xilinx RF SoC, which within a single chip here we have a 16-channel transmitter and a 16-channel receiver, synchronous, multiple gigasample, gigahertz capabilities. And this is something 10 years ago we would have in a big rack in the P3 to have these capabilities. I'm going to look at two different kind of scenarios with using drones. One is, how can we use drones to provide useful data collection in situ, sled-based or local observation. This would be using small to mid-sized drones to look at areas where we can have a camp near where we want to collect data, and it provides us with potentially faster survey speeds and the ability to load waypoints to facilitate grid surveys. Kind of on the other end is long-duration regional surveys, where we could potentially reduce the logistical cost. However, the performance compared to what we were able to get with maybe the P3, the Basler, the Twin Otter, we might not be able to match that. But we do have the capability to fly lower with these and slower to provide longer integration times and reduce surface clutter. So, some recent activities from scouring the web, looking at journal publications on presentations or journal publications on the use of drone-based radar. One, Jensen and Jacobson used this custom, fixed-wing system here that they strapped a ILM Sense UAV sensor to, and were able to measure snow thickness up to 4 meters here, it looks like. Prager et al. Used the DJI DJI Hexcopter, along with a software-defined radio and a companion computer. Tan and Al used over on the right there a octocopter with a 1 to 6 gigahertz VNA, vector network analyzer, to collect some measurements. And finally, Vergnano et al. Used a drone-borne GPR to get measurements of snow cover. And if we look at these, what we see is most commonly these are hexcopters with third-party SDRs or sensors that we use to take the place of a GPR. There are also commercial systems available. We have UGCS drone GPR, Mela drone GPR, which essentially strap GPRs to hexcopters. And then also there are non-sounding systems, and this is IMSAR, which provides a number of Ku-band systems, which are side-looking imaging radars. And we see those here. Moving on with decreases activities. These are some rather interesting results that was accomplished through a NASA project that was funded just before the pandemic happened. NASA came to both Vanilla, who manufactures this UAV, and Creases to put our snow radar onto this platform. The radar was a system that was originally developed for the 2013 Misopex project. It never did fly on that due to losing the aircraft before the radar was flown. It was modified to fit on the Vanilla UAV. The Vanilla UAV platform is designed and managed by Vanilla Unmanned Platform Aerospace. The very interesting thing about this platform is it has a 10-day endurance. And so it can take off and loiter, go survey for 10 days. It has wing hardpoints for the antenna pods, and it's truck launched. But they are working on a VTOL system for this. Over on we see the system from a chase plane, an onboard camera of the system, and this is the radar system that was integrated into the nose bay. Some not so recent activities from Creases, and this is kind of leading up to some of the lessons learned. Through NSF funding and this Creases Center, we started out early on with developing this 1,000-pound UAV to go do wonderful things in Greenland. And we developed the system, we took it out for some flights, we got some preliminary data from Greenland where these are ground-based measurements from NEAM, and we performed a few airborne flights and got some indication that we were able to measure the bedrock, but nothing really panned out with that. Took it down to Antarctica, and we say we had a hard landing, but we essentially had a crash on the McMurdo runway. And then we stopped work on that just because we found it was too much having students and faculty that are rotating in and out to operate the system. The consistency wasn't there. So we moved on to smaller UAVs, and this is a G1X system, which is a commercial airframe that we modified, integrated HF antennas into the wings, and we're able to perform measurements over Southern Glacier in Greenland, KNS Glacier, and get some measurements. Here's some previous M-Quartz sounding of it, and you can see with the VH system we were able to get measurements with this system that we were not previously able to measure. So some of the lessons learned, operating in polar regions, we need very accurate weather forecasting and anti-icing strategies, especially for the long-range system. Navigating near the poles and communications with the system, especially beyond line of sight, is difficult. Low altitude operation has risk in mountainous regions, and we need some way to automatically shut off the radar. In terms of radar integration, if we look at most systems nowadays, they're carbon fiber. And attaching a VHF antenna or HF antenna to a carbon fiber structure is not easy. So thinking about that, the platform and the radar need to be co-designed or have multiple wing hardpoints that we can put pods on. And also there's a lot of potential for radar comms interference and comms radar interference. How can UAVs, how does this fit into rings? And so if we think about what we have previously had with rings, and maybe I should have the Twin Otter up here as well, is that we have these big manned aircraft with large arrays, and what we want to do is fit that on something like maybe we have here with the NASA Sierra system. A couple of potential ideas for this, going back to our small local scale, is to have a VTOL system that we can have a remote field camp and operate that with just a few people, or kind of go to the other end in equipping some of these larger drones with high power radars and flying from a more permanent field base where we can transition a great distance. And so finally, that's the last slide. We did submit a proposal to NSF to develop a sounding system to go on this vanilla platform. We haven't heard results yet, but we're hoping that is funded, because I think that might provide a interesting link to getting something with rings. And so I think I'm a little bit over time, but